Hello, so in this video we're going to be talking about the first method of how we can solve a non-homogeneous system of linear differential equations, and it's going to be based around this idea of diagonalization. Now I have already talked about diagonalization, so hopefully this should be just a little bit of a reminder. Perhaps there's a few new things in here as well, but you know, if anything, it's always good to go over things which we've already done, perhaps in a little bit more detail and seeing how it's implied. Okay, so basically we've got a non-homogeneous system which has been collapsed into matrix and vector notation. Okay, it's a linear system, and it's been collapsed, you know, in the familiar form. So we've got, and it's non-homogeneous because we've got this plus k on the end there. Okay, and basically I'm considering a 2 by 2 case. So in other words, I'm considering dx by dt equals some linear function, you know, ax plus by plus k, yeah, k1, and dy by dt equals, you know, cx plus dy plus k2. So that's where these coefficients are coming from: the a, the b, the c, and the d. It's just this table of a matrix of these coefficients. All right, so you've met this before, and it will always be an n by n matrix. That's fine. Now, from this, as I've probably seen this before, you can pull out eigenvalues. So you can pull out eigenvalues, and there'll be you know, the number of it's an n by n. It's a square matrix basically, and the number of, you know, the n, if you like, the number of rows, number of columns, corresponds to the number of variables, so therefore it corresponds to the number of eigenvalues you get out. And for each eigenvalue you can get out an eigenvector as well, and I'm going to call them u and v. Alright? And the idea is, I mean, you've met this kind of thing before, we're going to use these eigenvalues and these eigenvectors to basically make A into a diagonal matrix. So in other words, a diagonal matrix is one where there's only numbers, there's only elements on the leading diagonal. The other elements are always zero. Okay, so that's what we want to basically do, is we want to turn A into this thing here, because of course the reason why we do that then, because if you look back into our original system up here, oops, sorry, maybe if I write it down a little bit clearer down here. So we've got dx by dt equals ax plus by plus k1. Yeah, and dy by dt equals cx plus dy plus k2. And the reason why I want to make A, you know, a matrix A, a coefficient matrix A, diagonal, so in other words, there's only elements here and here on this leading diagonal, you know, these elements will basically disappear, is because then, as you can hopefully see, this system becomes just essentially a linear, or these equations, you know, this dx by dt and dy by dt, just essentially becomes a linear system, you know, which you're used to dealing with. So dx by dt equals ax plus k1. There's no y involved in that equation. And likewise for y, you've got dy by dt equals dy plus k2. There's no x involved in that equation. So in other words, what you're doing is you've only got the variables which are relevant to what you're differentiating with respect to. So here you're the elements you're differentiating. So here you're differentiating x, and there's only a linear equation involving x on the right. Okay, there's a constant, but that's fine. You know, that's why it's homogeneous. And likewise for y, you've only got a y on the right-hand side. Okay, so that's essentially what you want to do, is you want to try and get rid of the kind of the non-corresponding, you know, you want to get rid of the y in the x case and the x in the y case, okay, and that's sort of in general. So you're only basically dependent on one variable. And that's called a diagonalization. And the way which you're going to do that is you're going to basically going to boil this A matrix down into the things which, the kind of the defining characteristics, I call them. And they're basically the eigenvalues and eigenvectors. All right? So, you know, I have talked about this before, but let's go through it again. Right. So, what I want to basically do is I want to form two matrices. Okay, so we've got our eigenvalue. So we've got A. Let me just write A out again. So we've got A, B, C, D. And then from that, we've got eigenvalues, lambda 1 and lambda 2, and corresponding eigenvectors, and I'm going to call them U and V. Okay, so the U is the eigenvector corresponding to lambda 1, and V is the corresponding eigenvector to the lambda 2 eigenvalue. Okay, so what I want now do is form two matrices. So I want to form a diagonal matrix which is based on my lambdas. So lambda 1, lambda 2, and the other elements are 0, right? And I also want to form, and that is kind of the general, you know, when you solve eigenvalues and eigenvectors, you only consider the leading diagonal anyway. So that's the reason why I'm writing that, you know, my diagonal matrix like that. Yeah, if you're not sure, go back to the eigenvalues and eigenvectors video, which I've done, or any video which on YouTube, or even just go back to your notes and and just remind yourself that that is what you do. You only when you're solving the system AX, the system to find eigenvalues and eigenvectors, you only consider the matrix which has the leading diagonal. All right. Okay. So that's my diagonal matrix. That's called D. And I also want to form another matrix which consists of my eigenvectors. So I want to consist of U and V. Okay, but I'm going to break my eigenvectors up into the elements. There's going to be two elements in my eigenvector. I'm going to have U equals U1, U2, right? And I'm going to have V equals V1, V2, right? So I'm just going to basically form a matrix out of the columns, where the columns consist of each eigenvector. So this is U1, U2, and this is V1, V2, right? Okay, so these are now my three matrices. These are now my three matrices that I'm going to be considering in this video to make my A into a diagonal matrix. All right, so essentially, what I want to do is I want to start off with, I want to find a solution to, remember what I'm trying to do? I'm trying to find a solution to my homogeneous system. Where is it? That's what I want to find a solution to. Well, the first thing I'm going to do, just like in my case, if you've watched my video beforehand, the first thing I want to do, the solution to this, my solution to this would be x equals, it'll be my complementary solution. So the solution to my homogeneous case, so in other words, with no, what's going on here? With no x, right? And plus a particular solution, so a solution which is based on a guess of what my k looks like. All right. So first thing I want to do is I want to find a complementary solution. So first thing I'm going to do is try and solve a solution for the homogeneous case. All right. So with no k on the end. So I want to try and solve this thing, dx by dt equals ax. Right. Well, I can do that because ax, remember, if you remember how I solve eigenvalues, right, or my eigenvalue and eigenvector problem, this is what I'm trying to solve, right? Ax equals lambda x. So in other words, what I can say is that when I do a times x, remember my x is just my variables, right? X and y. My x vector is just my variables x and y. Yeah. So I want to solve a times x equals, so I'm just looking at this equation here now, ax equals lambda, and that's going to be lambda 1 times xy. All right, and these two, these two vectors here, of course, are the same, will end up becoming my eigenvectors u and v when I solve the problem, right? So what I'm basically saying is that because my derivative is equal to this, it's also equal to lambda x, right? You happy that that ax is the same as that ax there, and that ax is equal to lambda x. Yeah, so this is what I'm basically considering now. I'm considering this right-hand side of my system here. Okay, well, of course, I know what my matrix A is. It's A, B, C, D. It's my coefficient matrix. All right. So I guess what I'm trying to say here is I'm trying to show you, hopefully you've seen the link that, what we had was dx by dt equals ax. Yeah? Well, I've just used the eigenvector and eigenvalue equation, so ax equals lambda x, basically, and seen that, ax is equal to lambda x. So in other words, this thing, dx by dt, is also equal to lambda x. So in other words, the eigenvectors will determine the solutions. Yeah, because what I'm after is x. Yeah, I'm after x and y. So what I'm after is x. Okay, and x, basically, what are x? Well, they correspond to the, they will become the eigenvectors u and v. Yeah? So my eigenvectors u and v will essentially form the solutions. So in other words, my trajectory, that kind of makes sense when we're talking about equilibrium points and such like, this kind of path of trajectory. So what I'm basically saying is that, if I can find u and v, so if I can form a matrix of u and v, then that can help me determine what the actual solutions are going to be to the homogeneous case. And that kind of makes sense because I have, u and v, okay, and, if I draw that geometrically, so I draw them like this. They can lie anyway, the angle is kind of, I'm just trying to show you for convenience. And there'll be an equilibrium point. There's always an equilibrium point where they cross. It could be stable or unstable. And essentially what's going to happen is that if, x, because x is a solution to this dx by dt, dx by dt equals ax. My x is a solution to this equation, because that's the thing which I'm after. That's the thing which I'm trying to find. The path of x will be determined by v and u. I've talked about this in previous videos, that basically we use the eigenvectors to determine what the solution is going to do. But this is the reason why. Because, I can write ax as lambda x. I can just basically use the eigenvector equation to just basically solve this. Yeah. So in other words, I just need to find the eigenvectors, and I'll be able to, determine what my solution is going to be doing. So it's going to be determined by this. So essentially, if I put these eigenvectors together into my matrix, which I have done up above, so u1, u2, v1, v2. So that's my matrix of eigenvectors. Okay. Then the path of this will vary by some value or multiple, by some value or multiple of u1 or u2 or u or v, essentially. Okay, so in other words, if I say, well, look, x is going to be determined. Right, let's just start again. Let's try and get this in our head. So x, my solution, is going to be determined by my eigenvectors. And my eigenvectors I can model as t. Yeah, because obviously my solution, this is my solution, say. And let's say I start at x and I want to move towards u. Yeah, so I start at x and I want to move towards u. So start at v and I want to move towards u. Start at v and want to move towards u. This is my solution vector x. Right? And so this is what I'm doing here. So I've essentially formed a saddle point, for example. Okay. Well, basically, in order to do that, I can model, exactly what's going on up here. It may be that. It may be a stable node or something like that. I'm just using this as an example. I can model that just by multiplying it by some value. I'm going to call that p. I'm going to call it p, because look what happens. I've got t here. Okay, and let's call p p1, p2. So p is p1, p2. Okay, and so now if I multiply t by p, what do I end up with? u1, v1, u2, v2. So p1, p2. All right, and I multiply this out. So what do I end up with? I end up with p1, u1 plus p2, v1. Yeah, and then I end up with p2, u2. Is that no p1? u2 plus p2 v2. Yeah, and so that's what I end up with. So basically, just by selecting which values of p and p1 and p2 I need, if you look, because p1 will always correspond to the u vector, and p2 will always correspond to the v vector. So essentially, if I make p1 bigger than p2, for example, it's p1 bigger than p2, I'm basically making my solution, as t gets bigger, I'm basically making my solution tend towards u. Yeah, I'm making my solution tends towards u, which is exactly what's happening up here. Yeah, I'm making my solution tend towards u because I'm making p bigger. So essentially, I'm basically just getting rid of p because I've made p1 bigger than p2, for example. So I've made I've made u the dominant vector. But if I make p2 bigger than p1, yeah, I'm making v the dominant vector. So basically, just by choosing carefully my values of p1 and p2, I can model this, this kind of whole situation entirely by matrices. Now, if you remember before, I kind of modelled it using intuition, over time and such like. This is exactly the same as what we've got before. Exactly the same as what we've got before with types of equilibrium points and stability of points. It's exactly the same ideas, but now I've just been able to represent those ideas as a matrix, or as vector and matrix notation. So now x, as you happy, go through and convince yourself that x is satisfied by this equation here. By this equation here, x equals our transformation matrix, which is just our vectors, multiplied by some matrix or some vector p. And that the choice of the value for p, so the choice of the value for p1 and p2, will allow me to either move towards u1 or move towards move towards u or move towards v. You know, it will allow me to choose which vector I can move towards. If I make, for example, P1 bigger than P2, I'll move towards U. If I make P2 bigger than P1, I move towards V. So essentially, just by choosing P, I can make sure that my trajectory, which of course is my X, you know, my X, this path here, or these paths here, are just basically modelling what my solution, X, is doing. So just by choosing P carefully, I can make sure that X is, you know, X follows the path which I want just by choosing P carefully. So I can choose which eigenvector and eigenvalue, which of course is contained within T. I can choose which eigenvector and eigenvector, which of course is the matrix T. Yeah, I can choose which eigenvector X will move towards just by carefully choosing P. Yeah. So are you happy then? Hopefully I've made a good enough argument that this will model our solution. This X equals TP will satisfy our solution. Yeah, because TP will just model exactly what X is doing, and X is just our trajectories. Right, X is just our trajectories. Okay, so X is just, you know, so X is satisfied. Let me just write it down again. So X is satisfied by TP. Okay, so now if I let X equals TP, remember what I'm trying to solve. I'm trying to find a solution now to, so that's a solution to my homogeneous case. That's a solution to my homogeneous case. So if you like, this is my my complementary solution. Yeah, it's my solution to my homogeneous case. But now I want to try and find a solution to, you know, I want to find the whole solution by finding a particular solution. So in other words, I want to, so first thing I need to do, just like you did with ordinary, you know, nth order linear ODEs, you know, which you're used to solving, go back and watch them, if not right at the beginning of this course. So now what I want to solve is I want to plug this back in to the non-homogeneous case to try and now find that extra bit, that particular solution. Okay, so I want to plug this X equals TP back into here. Right, so first thing I want to do is I want to differentiate this thing. So I get, so d by dt, okay, just replace it with, whenever I see an x, I just replace it with TP, right? So TP equals A, TP plus K. All right, so let's look at this now. So what do I get from here? Well, what's the derivative with respect to t of dp by dt? Sorry, d by dt of TP, right? Well, it's going to be, well, T, my transformation, my T matrix, if you remember just my matrix of eigenvectors, they're not going to vary over time. Eigenvectors aren't going to vary over time. They kind of remain constant, yeah? They just remain like that. They don't change over time, right? So I can't differentiate T with respect to time because the eigenvectors aren't dependent on time. Right, so T, if you like, is just a constant. And so what I'm left with is dP by dt, okay? And likewise, what have I got here? Well, I've got ATP plus K. Then essentially all I'm just trying to do is solve this system. So first things first, I want to get dP by dt on its own. So I'm going to take T over the other side. But remember, T is a matrix. T is a matrix, so I can't just divide by T. I can't divide by matrices. I have to multiply by its inverse, right? So dP by dt, then, you know, and T inverse times T is just the identity matrix, which is just equivalent of 1. So when I multiply T inverse here, I just essentially can get rid of that. Yeah, so T inverse there, so I end up with T inverse AT times P plus T inverse times K. All right? Okay. Now, if you remember that in the last video, or my diagonalization video, so I'm not going to go over it here, that this T inverse A times T was just my diagonal matrix D. Okay, and I proposed an argument for that. I basically considered, okay, what was it? I think TD equals AT. Yeah, and I solved this system basically. You know, go back to my diagonalization video and you'll be able to see that. But this is T, and I'm just going to call this thing on the end, just to tidy it up a little bit. I'm just going to call it M, just for convenience. It's going to be some matrix M. All right, because it's a vector times a matrix, so it's just going to be M. All right. So, what am I left up with? Well, I'm left up with that dP by dt equals dP plus M. All right, so that's a little bit nicer. But look what I've got. More crucially, look what I've got. Okay, I've got a plus m on the end, but I'm not really too worried about that because I've got exactly what I want. I've got my a now. You know, if I compare it to the form of dx by dt, what I started with, equals ax plus k. You know, my matrix here, which is multiplied by a vector. Okay, fine. I've had to change my x into a p, but that's not an issue. Okay. That's just another vector, okay. And likewise, I've sort of changed my k into an m. You know, if you just compare the forms, but look what I've got here. Look what I've got here. I've got a diagonal matrix, which is exactly what I want. You know, okay, fine. I've had to change some other terms. I've had to change my x's and k's and things, but I've got a diagonal matrix, which makes it far easier to kind of try and solve. So I've got a diagonal matrix. All right, so all I've got to do now then, I've got a diagonal matrix here. All I've got to do now then is try and find, I've got to now try and find what P is. So in other words, what my values are, if we go back to what P was, the idea of what we're doing with P up here. So in other words, I need to find the values of P, which will make my system behave in the required way. I need to find P1 and P2. All right. So what have I got? Let me just say here, my diagonal matrix is, what is it? Lambda 1, lambda 2, 0, 0. Okay, if I just consider the dp part for the moment, yeah. And then my P matrix is P1, P2. Right, so that's equal to P. That's equal to that, and then plus M, which I'm just going to break up into M1, M2. Yeah, it's just some constants. Okay, so let's multiply this out. So we end up with lambda 1, P1, right, plus 0 times P2. And then I've got 0, P2, plus lambda 2 times P2. This is plus M1, and this is plus M2. So I've just literally multiplied that thing out the bottom, out the end. Well, look what this is equal to. Just remember what this is equal to. This was equal to dp1 by dt. Yeah, this is just, I'm just multiplying out this dp by dt now. dp1 by dt, and this thing was equal to dp2 by dt. Okay, well that's exactly what I wanted. Okay, fine, I've had to have p1s and p2s and things, you know, instead of x's. But look, I've got a p1 here. I've basically just got a system that involves only one variable. Yeah, so I've got p1 there, I've got p1 here, I've got p2 here and p2 here. I don't have to worry, so that's p1, that should be p1. I don't have to worry about anything else. I just got exactly what I want. So I've managed, by diagonalization, I've managed to get exactly out. I've got exactly what I wanted. All right, so essentially what I've got now, if I just write this out again just slightly neater, so dp1 by dt is equal to lambda 1 p1 plus m1, all right, and then dp2 by dt equals lambda 2 p2 plus m2. Yeah, that is an ODE which I can solve. You know, these two things are ODEs which I can solve. Okay, I can solve this. Yeah, I can solve this really, really easily. And so therefore, once I've, you know, I can solve this, I can find out what P1 is, and I can find out what P2 is. Yeah, so essentially I've diagonalized my system, I can find out what P1 is, and I can find out what P2 is, and then I know that X is satisfied by TP. Yeah, so in other words, X1, X2, if I just write it out in proper matrix notation, T, remember, was U1, U2, I know that, and V1, V2, I know what those eigenvectors are, and then I've got P1, P2, and I've just worked out what those are. So in other words, I know now everything on the right hand side, or at least I've got techniques to work out everything on the right hand side, and so therefore I can just read off directly what my solution for X is. Okay? Perhaps this kind of thing is quite abstract. I mean, I've tried to kind of illustrate the ideas as best as possible. But you know, perhaps it's better seeing as an example. Okay, I mean, essentially what I've managed to do is convert. Let me just run you through a sort of a summary. So dx by dt, okay, equals ax plus k. That was a non-homogeneous case that I was trying to solve. So first things first, we managed to find a solution to the homogeneous case. Yeah, because ax is going to be equal to lambda x. Yeah. Just by looking at that thing there. So I managed to find a complementary solution, essentially. All right. Then what I was able to do is by diagonalization, I was able to turn this thing, dp by dt, into a diagonal matrix times P plus, you know, some matrix on the end times M. And essentially that is, you know, that was a system that I was able to solve, you know, because it only depended on one variable, so I could solve that. Okay, granted, if you've got loads, if you've got like 200 different variables, that's quite difficult to solve. But if you've only got a small system, you know, that's absolutely fine to solve. Absolutely fine to solve. If you've only got a system of, say, like 2 or 3 equations, that's absolutely fine to solve. Yeah, because it's essentially just 3 ODEs that you could just consider separately. All right, and then basically you can get from that, you can find out what P is, and you know that X is a solution of our eigenvector matrix times P. All right, so I can just plug that back, you know, my values for P back into here. I know what T is, and so therefore I can just read off directly what X is from there. So that's the whole idea of what we were doing in this video.